So for our derivatives of our trig functions, we're going to start with sine and cosine. Then we're going to move on to look at tangent and some of our reciprocal functions. But to start off, we're going to look at some GeoGebra applets of these. We're going to start with sine. There's our graph of sine from 0 to 2 pi. Now it's from 0 to like 6 pi. If I take a tangent and draw it on there, the tangent of sine right when we start at 0, 0, can you see that I've got a little bullet at 1? That is the slope of the tangent there. Now if I drag this point along, can you see that my slopes, they start at 1 here and they start to flatten out until they get to 0 right there. And now as I keep going, now all my slopes are negative. The steepness is getting greater and greater and greater until it gets to pi, and now they're starting to flatten out again until we get to here where it's 0 again. Now if we kept on going and doing this over and over again, we would make a graph of all of those slopes. And looking at that, do you recognize that graph? So the sine graph is the black one, and the blue one is the cosine graph. So if we look at our notes, that's the first one. If we have the function y equals sine of x, the derivative is cos of x. And if we think about what's happening to those tangents, if I start this over again and clear it up, we're starting with a positive slope at 0, 0. As we go to pi over 2, we're going to get to a point where our tangent is flat. In fact, wherever there's a maximum or a minimum, your tangent line is going to be horizontal. From pi over 2 all the way to the next time that it's flat, all of these slopes in there will be negative. You see that that tangent line is always going downhill from left to right until we get to that. So all of our values for our blue graph, they're all negative. And this continues over and over again, and sure enough, it matches up with our cos graph. What do you think is going to happen if we started with our cos graph? So let's look at, here's our cos graph to start with. Can you see that your cos graph starts right at a maximum? And so it's going to have a derivative at 0 to begin with, because the slope of a tangent that is horizontal is 0. Before we do it, can you see as I go from 0 to pi, the next time that it's going to be 0, that all of those slopes between 0 and pi are going to have negative values? All of the tangent lines, as I go this way, are going to go downhill from left to right. And so as a result, everything between 0 and pi will have negative slopes. So when you graph the derivative is below the x-axis. Then everything from pi to 2 pi, can you see that all of those tangents would have positive slopes? So if I would start at pi and then just go between pi and 2 pi, all of those ones have positive slopes. And if I did this all the way along and kept going and drawing those points as I went, missed a few in here. There we go. We get a graph. This isn't a sine graph, this isn't a cos graph perfectly, but it is a transformation of those. How would you describe that blue graph best? Can you see it as a sine graph that's been flipped over the x-axis? So how do we show that transformation? As a minus sine x. So I hope that that graphical representation will help you remember what they look like. They're very similar because the derivative of sine is cos and the derivative of cos is negative sine. So remembering where the negative goes is going to be the hardest part because they're so similar. I always find for myself that going back and thinking of the graph, if I think of my sine graph and I draw a tangent right away at 0, 0, I'm going to get a positive slope. So the derivative of sine is positive cos. That's part of the way that I help remember it. And if I think of my cosine graph, so what I'm saying here is when I think of my sine graph, it's going to start off with slopes that are positive, and the derivative of sine is positive cos. But if I think of my cos graph, it's going to start off with tangents whose slopes are negative. And so that helps me remember that the derivative of cos is negative sine. So now we can do all of our derivative rules that we've learned up till now and include trig functions in there. So now we can have trig functions with the chain rule, trig functions with the product rule. And all we're adding is we know that the derivative of sine is cos and the derivative of cos is negative sine. So here's our first one. Now one thing about the power rule and sine and cos, because you've experienced this before because you've done sine squared plus cos squared equals 1, and when you write sine squared and cos squared, you're used to writing the squared in between the sine and the x, right? When you wrote sine squared plus cos squared, you put the little 2 in between the sine and the x. Now what it actually means, if we wanted to, we could rewrite this. This means sine x all to the power 4. But we write that 4 in between the sine and the x. The reason we do that is so we don't have to include brackets. The other reason that we do that is so that we can tell the difference between sine x all to the power 4 and sine of x to the power 4 when just the x is getting to the power 4. Mathematicians don't like to write brackets. So in order to decide between these two and not have to write the brackets, they decided to write that 4 inside there, and then it's all solved. We don't need to write brackets, and we just have to learn this is a specific type of notation. What makes this a little bit difficult for doing our derivatives is that when it's written in this form, the chain rule, we always did the outside function and then multiplied by the derivative of the inside function. Sometimes when it's written in that top form, it's hard for you to see that the 4 is the outside function because it's sort of written inside the function. So if you want to take the time to rewrite it like this, then we can easily do the derivative. So the 4 would come in front. Subtract 1 from the exponent, and then multiply by the derivative of the inside function, and the derivative of sine is cos. If we write it in that kind of notation first, it's really easy, because we're just doing our normal chain rule. Then afterwards, if you would like, you could write it in proper notation. Well, this cubed, when I have it outside the brackets, it means sine x times sine x times sine x, because an exponent means repeated multiplication. And sine is a function, so we can't just say the sine is cubed and the x is cubed, because it's not like it's two variables. I think what you're thinking of is if you had xy all cubed, this is equal to x cubed, y cubed. Why isn't sine x all cubed equal to sine cubed x cubed? And the reason for that is sine itself is a function. It's not a variable. It's not a number. So when we write xy, xy are variables, and both x and y could represent a number. But when we write sine x, the x is a variable, it could represent a number, but sine is a function. It doesn't, sine is never a 2. So you can't just think of it as that. Yes? If you wrote it like this, I'd accept that. Okay? If you're looking at your answer keys in the back of your book, they're going to have it written in this form. And it's important just to know that this and this mean the same thing. So I'd like you to try this one on your own. So to recognize that this is a chain rule, that the 3x cubed is inside of cos. So if we're looking at our outside function as cos, that's the first derivative that we would do. The derivative of cos is negative sine. So we would write negative 4 sine. You don't change the inside, it'll stay 3x cubed. Then the chain rule says once you've done that, now we multiply by the derivative of the inside function. The inside function is the 3x cubed. The derivative of that is 9x squared. So recognize what's our outside function. Do the derivative of that first. Keep the inside the same while you do that. And then afterwards, multiply by the derivative of that inside function. So here I kept the first one the same. The derivative of cos is negative sine. Plus, keep the other one the same. The derivative of 3x7 is 21x to the 6th. So here's a show that question. We're starting with y equals sine x cos x. We want to show that the derivative of this is going to be cos 2x. How do we go about this? How does this work? I'm going to prove this in two different ways. Now, cos 2x, sine 2x, that's going to remind you of some things that you did with double angle identities in grade 12. I've got a bunch of the formulas up on the board over here. But on the exam and on the tests, those ones too, you'll need to memorize them. So you'll have to know that sine 2x is 2 sine x cos x, that cos 2x is cos squared x minus sine squared x, and how to use those identities, because in this case we're going to need to use some of them to do this proof. The most simple way to go about this is say, well, what have we done every time that we've had to show that question? We start by doing what we know, and then we manipulate things algebraically until we come up with the answer. So I'm going to start that one this way. I'm going to start by saying, well, f prime of x, here we have a product rule because I have sine of x is one function multiplied by cos of x, a second function. So I can keep the first one the same, multiply by the derivative of the second one. And the derivative of cos, negative sine, plus keep the second one the same and multiply by the derivative of the first one, and the derivative of sine is positive cos. And now comes the algebra part. I need to take what I have here, manipulate it so I end up showing cos of 2x. Now cos of times cos, that'll be cos squared, and sine times negative sine will be negative sine squared. And sure enough, that's one of our identities. Cos squared minus sine squared is cos of 2x, and you've showed it. You can write the fancy Latin initials. We've showed what we wanted to show. Yes? So a second way to do this proof is to say, I want a cos 2x. If cos 2x is supposed to be my answer, and I know that the derivative of sine is cos, maybe if I had a sine 2x to start with, then I could get a derivative of cos 2x in the end. There comes the recognition of, hey, if I have sine x cos x, that's awfully similar to a formula that we have. One of our other double angle formulas is that sine 2x is equal to 2 sine x cos x. That's very similar to what we had to start with, except the 2 is not in front. If I wanted to get rid of that 2, I could just divide both sides by 2. Now when you divide sine 2x by 2, it's the same as multiplying by a half. You cannot simplify the 2 that's inside the sine with that dividing by 2. Because that 2 that's inside of the sine is part of that function, whereas dividing by 2 is just like having a half out in front. It doesn't apply to that value inside the function. But if I did this, then I've just rearranged my original formula and said y is equal to 1/2 sine 2x instead of y equals sine x cos x. Now to do the derivative of that, it's no longer a product rule, but now it's a chain rule. My outside function is the sine, and inside of sine I have another function which is 2x. So how do I do a chain rule? Do the derivative of the outside first. The derivative of sine is cos. Keep the inside the same. Then multiply by the derivative of the inside function. What's the derivative of 2x? 2. Now, if we had done that originally, the 1/2 now times the 2, those will both simplify. And we've proven it that way as well. So there's often many ways that you could show the same thing, especially when you have identities involved. When you introduce an identity, how you introduce that identity will help you solve it. In this case, I think the first method is more typical because you know that you need to find the derivative, so most of the time you will do that first and then use your algebra to manipulate it till you get what you want to show. But this is a case where using an identity to begin with made our question into something that the derivative followed naturally to what we wanted to get. Both are important skills to have because in some situations, doing that little thing at the beginning will make your question way easier further on. So to be aware that sometimes you can do those things can help you make the question easier. Other times, doing something naturally the way that you would do it normally is still the best way. But it's important to know you have both of those options and to be able to, if one way starts to become too difficult for you, then you might take a break and go back and say, maybe there's a different way I could start this question that'll make it easier. All right, so this one, straightforward. We've got chain rule. The outside function is cos. Derivative of the outside is negative sine. Keep that the same. Then multiply by the derivative of the inside, which is 12x squared. No problem. For the next one that you've tried already, here I would take the time to change things. So I have 1 over root x. I'd change that first to x to the negative 1/2. Just going to make my life a little bit easier. So I don't have a quotient rule inside of a quotient rule. It's doable, but not as much fun or not as straightforward as this. Now we just have chain rules inside of quotient rules. So the quotient rule says keep the bottom one the same. Keep the bottom one the same. Derivative of the top. Derivative of the top is chain rule. Outside function is cos, so that'll be negative sine. Keep the inside the same, then multiply by the derivative of the inside. Subtract. Now we keep the top the same, and we do the derivative of the bottom. Another chain rule. Our outside function is sine. The derivative of sine is cos. So we get cos x to the negative 1/2. Then the derivative of the inside will be negative 1/2 x to the negative 3/2. Too much brain spinning? Overheating? And then you take the bottom and square it. Yes. Yeah. So when you go to your textbook, this one will be simplified because this will have a square root of x cubed on the bottom, and they'll write that answer on the bottom. So when you're going through your homework and you're doing the show that part, then you're going to see, oh, I have to simplify this one a bit. Okay, we're going to go back to this one because we noticed we made a mistake. We just did this, right? We ignored that sign because nobody really wants to deal with that sign out in front. And we just did the derivative of the right. If that sign is there, how does that change things? Well, then it becomes implicit differentiation. So you have to do the derivative of the left side and the derivative of the right side. And what will that look like? Well, the right side is going to stay the same. We already did the derivative of the right side. I'm going to take this. I'm going to move that over. Ooh, this is pretty. Move that over here. Move this with it right there. Didn't want to do that, but that's okay. And now we just have to, what happens when I do d dx of sine y? Okay. Derivative of the outside function is sine. Derivative of sine is cos. So you'll have cos y, and then the derivative of the inside will be dy dx. So our final answer, working on this. That's what I wanted. Maybe not. No. I was trying to make things easier by copying and pasting, but it's not letting me do that. dy dx is going to equal this whole thing on the right, 3x to the 7 times a negative sine x plus cos x times 21x to the 6 divided by cos y. Well, we're not going to simplify that. So that's when when we did notice, oh, there was a sign in front there. That makes our life more difficult. We had to use implicit differentiation to solve that. Wasn't that bad for the implicit differentiation on the left, right? You do the outside. Then whenever you have just a y, you do dy dx at the end. And we'd have to divide by cos y. If you wanted to get y by itself in this, you could. Because what's the opposite of sine? Sine inverse. So then you'd have y equals sine inverse of 3x to the 7 times cos x. But then you'd have to know how to do the derivative of the inverse sine, which we don't yet. So we would do this implicit differentiation instead. Yeah, tan's coming up. But thank you for leading into that. That was perfect.